Hey guys, hope you're doing well. Happy Earth Day to those of you who are celebrating it, even though we're kind of stuck inside at the moment. Uh, yeah, always important to keep the environment healthy, and we're doing that right now by all staying inside. So what I'm going to talk about this one is just Lab 8, trying to go forward and kind of think about how to go ahead and do this lab because it's a little bit longer than usual, but there's not as many problems. There's just a lot of reading and stuff there, but I just want to talk about the concepts prior to it a little bit to hopefully help you guys out going forward here. So let me share my screen. I'm just going to do some writing first. Whenever we're thinking about going forward and trying to come up with limits of integration, this is all about triple integrals here, right? So we're going to come up with limits of integration. How do we come up with different values? So if I have some, there's some volume here, right? Some nice little volume that could be described in many different ways. Maybe it's like a cylinder here. And I want to come up with the limits of integration for something like this, f of x, y, z, dv. And again here, what we're going to try to do is come up with the limits of integration for this kind of object here, right? I want to think about how I need to go in terms of dx, dy, and dz. Which order do I need to put these in? Do I need to integrate with respect to x first, y, or z? And the ways to kind of do that are many times going to be kind of a personal approach, because there's many different ways we can. There's 3 different types of integrals that we can kind of create. We can kind of do dz first. We can integrate out z, which means that we need to find 2 functions that are bounded above and below that are functions of x and y here, and another function of x and y. We're bounding by x and y here. What does that mean? Well, that means as I draw arrows going up through my domain here, I need to see where I enter the region from and where I exit the region from, in the same exact way we have for type 2 regions. And in this case, for instance, for this one, it's actually pretty nice to see because it's more like a cylinder-esque thing. So we're kind of just going through the XY plane and going out of the top of that cylinder. So we might be able to describe this pretty well using DZ first. You can kind of, this is called a type 2 region, a type 1 region, sorry, type 1 here, a type 1 volume. We also have 2 other types. We have a type 2 and a type 3. That's when I have dy first. I'm sorry, dx first, my apologies. So which means that I'm going through my region here in the positive x direction, so coming through this direction here. We see that's probably very complicated for this kind of object to think about where we're entering and exiting from, because we're entering and exiting from the same exact volume here. And then lastly, a type 3 region is when we integrate with respect to y first. So going through the region in the positive y direction like this. And again, this is probably pretty difficult too. So usually there's going to be a nice, a nicer region to kind of draw this in, kind of think about with respect to z, with respect to x, or with respect to y. And it just comes with thinking about the geometry. There are some aspects of coming up with the bounds, some regions that actually very benefit from, looking at it from all different types of ways. And that's kind of what the goal of the first 2 exercises in the lab are, is to take a certain region, which I'll show you actually in 2 seconds here, and to kind of look at it from a couple different ways to see if we can write limits starting with respect to z, for instance, and then depending on which one you want, with respect to x first or with respect to y. Now, once I've integrated out z, what do I do, right? Once I've integrated out one of the variables, what I do is I project the surface, and this is what's going to be the big thing to come up with. Once I figure out the height of the object, what's the easiest way to think about the height? In this case, it would be the z. I project the surface down. One way you could think about that is by viewing this surface from the top. Right? Let's say I integrate this out with z. I want to think about this from the top. What does it look like? And you can probably see that this would look something like a circle, right? In this pretty base example. And this is on the xy plane. And we'd like to think about this now because to create my x and y bounds, I now just figure out these bounds for the circle. Now, as we had talked about in section 15.7, we could think about this maybe in cylindrical coordinates, right? Where I have r, theta, and z, right? And I could think about if this, especially if I have the z coordinate, right, that's always staying the same, and I project it down and I have something that might be able to be thought of in polar coordinates, cylindrical coordinates might be very, very beneficial. In this case, right, what I then do is come up with my x and y bounds however I want to, and then that's how I kind of do it. But the idea is I'm projecting, or I'm thinking about it looking from the top here. So the viewpoint is actually a really interesting thing. That gives us a viewpoint of what it's going to look like if I'm, for instance, an eagle's eye view, right? Kind of all the way from the top. Now, we do have two other types of coordinate systems that we'll be talking about, right? We have the cylindrical coordinate system. Cylindrical coordinate system, coordinates, I can write cylindrical. I can just do that, Nick. And what this says is it tells me that if I give you a point here, right? If I give you a point, I can tell you the x, y, and z coordinates of it, or what I could do instead is I could tell you the z coordinate of it. That's fine. Z coordinate stays. What I'm going to do instead is I'm going to give you the polar coordinate for x and y instead. So kind of think about what the angle is between here and what the radius is to that point. And this is now r, theta, and z. And we can describe every single point like this that's on a cylinder. So just kind of think about this visually. Right, I'm starting here. I kind of go out to the outside of the cylinder. I go outside of the cylinder. I then kind of go around this circle to figure out where I want to go. And then I go up. And maybe this is my point that I'm worrying about. So I go out this way, I find my angle, and then I go up to this point. That's how I can kind of describe it. And it's very nice to describe things on cylinders too, going forward for like this. So, with this in mind, we can start to, come up with different limits of integration too. And the big thing I want to show you here, and this is actually a really important part of all of this. Let me actually share my, make sure go ahead and write this down here a little bit more formally. Let me actually show you something in the lab first, because it seems like my thing is working here. So let me share this. So here's the lab that we're going to be tackling. And in the cylindrical coordinate section, right, these first two exercises are all about just regular x, y, and z coordinates, Cartesian coordinates, but you're going to have to come up with a couple of different bounds for it. And that's kind of the goal of this. So, coming forward, exercise 1, I'm going to show you, make you draw out this region in Mathematica, which will kind of just do the code right here. And we're going to make you, think about how can I think about this as type 1? And then in exercise 2, think about what this is going to be into type 2 or type 3 region. Okay, what is it going to be? Is it going to be, you can either choose whichever one you want and kind of go for it. So choose your own adventure. Those little books back in the day that I always really liked reading. But this kind of shows you the different ways to look at it from a different perspective and come from that idea. So using cylindrical coordinates, there's actually this really, really nice, nicely written section here. Again, you don't have to do anything here, but it's really important that you read and understand how to use Mathematica to help you out, especially to come up with these limits. Coming up from the different top views, this is what I'm kind of talking about here. We're able to, in Mathematica, look from the top and look from the different sides to think about projections. And that's going to be really important to think about and a very, very helpful tool for Mathematica to help us use that. Now, the big thing that I want you to remember is when we change to cylindrical coordinates, our volume here needs to change to r dz dr d theta. Okay. Now, when you're doing triple integrals in Mathematica, it's exactly the same way as you want to. It's exactly the same way, making sure you go in from the outside all the way to the inside. So coming up back to here, if I want to integrate this right here, this limit, right? I'm going from x from -1 to 2, y from x to 4, and z from 0 to x plus y. If I want to integrate this function, let's say f of x, y, z, I want to take this part. I'm integrating with respect to z first because it's dependent on 2 variables, right? So it has to be at the end. And then I'm saying now I'm integrating with respect to y first because it's dependent on 1 variable. And so I'm going to be able to just integrate it there. And lastly, x is just a constant, so I'm able to integrate that last. Has to move from right to left. You have to make sure of that. Your answer should never have variables in it, right? It's in this case, it's going to be representing more formally, a density here. But if there's an integrand of 1, it'll represent a volume. So cylindrical coordinates coming down, making sure that you're able to, write down your limits here in terms of theta and r and z. But the idea here, especially with cylindrical coordinates, is once I've thought about my height, I project onto the xy plane, and I just think about this as terms of polar, and making sure you always multiply by r. You can use a couple different techniques here, right? We can utilize the same technique we did in lab 7, where we can input, f of x, y, z. We can actually input r cosine theta, r sine theta into the function itself. Or we can go ahead as this example does. This is x, y, z, and this function, and we're switching this to polar. What we do is we literally just take x and write r cosine of t. We take y and we do r sine of t. We then do z as z, and we remember that we have to multiply it by r. We must multiply that by the differential. So this is cylindrical coordinates. Now, in terms of spherical coordinates, this is really important here, this idea of spherical coordinates, because just in general, right, we a lot of times think about things as on spheres or balls or something like that, and we want to try to figure out what's the best way to kind of write this guy. Cartesian coordinates is really hard to write for cylindrical, I mean for our sphere. Even cylindrical is pretty difficult. It's not really nice to think about too, and many times we have an integrand with like x squared plus y squared plus z squared. We might want to think about maybe using spherical coordinates here. So in this example, let me actually go back to my whiteboard briefly here, just so we can I can write down something and kind of show you what this kind of is. So if I have my spherical coordinates here, so spherical, are we able to write this down? Whenever we get a chance, there we go. Cool. So what we're going to do now is think about what I want on a sphere, right? What are my three variables that I'm going to think about? The first thing I'm going to think about, one thing I could tell you, is how far away I am from the origin. How far am I away? Right? Think about this as very from astronomy base. Okay. What if I have a telescope and I see a star out in the sky? How do I tell it where you are? Right? How do I kind of think about it? Well, what I can do in one way is tell you first off how far away I am. We call this rho. And you could find via the Pythagorean Theorem, actually relatively quickly, that we can find that x squared plus y squared plus z squared is equal to rho squared. This is just an extension of the Pythagorean Theorem. And because of this, right, we have that rho is just the distance away. So this is always positive. Rho and r are always positive, right? We always say that. Now, what are the other two things I need to tell you? I tell you how far away I am. That now gives me a full ball of options, right? A sphere is basically just telling me the points this far away from the origin. And so what I could do now is, okay, what do I need to tell you now? Well, the first thing I could do, because I have the swivel chair, I can now tell you I'm going to face in which direction? In this direction, right? Kind of think about the polar direction. And which way do I have to face here? And that's the polar direction. This works exactly the same exact way as our polar thing. So we have that rho has to be greater than or equal to 0. We have that theta is the same thing as we've had in the past, which is from 0 to 2 pi. And then lastly, we have to tell you, okay, so I've told you how far away I am. I've now told you which direction to face. Maybe it's in this direction. But now I haven't really told you this direction, right? Where kind of my angle's at. Let's say the star's up there. I have to tell you, I want you to look up that way. And the way to do that is to think about the angle I'm making from the z-axis. It's actually this angle right here. This angle. Okay? It's that angle. So if it's this angle, we think about this as phi equal to 0. This is phi, okay? At this point, I'm at phi to be 0. This is called the Azimuthal Direction. It's a kind of a weird thing. And phi runs like this and goes all the way down to the negative z-axis. Now, I want you to think about why. So if I tell you up to here, this is phi equals pi, if phi equals 0, this right here, once I'm at the x-axis, I'm on the xy plane, is phi over 2. It's pi over 2, sorry, pi over 2. And then if I'm down here, it's pi. Now, does it make sense for me to go any farther, right? If I go any farther, I'm going to be pointing back in this direction, right? But that doesn't make sense because what I could do instead is I could just move my theta around. Like I could flip over this way. I could flip over this way and just tell you maybe a phi angle going here. So we always will have that phi here, this angle is always between 0 and pi. And the ways to find these, which is pretty nice. Usually rho is usually the easiest one. It's just kind of almost what the radius of the ball is, or maybe if I have concentric balls or something like that, I could tell you, how far it is. Like the radii that we have in polar. If I want to figure out polar, if I want to figure out this theta, what I do is I project onto the xy plane. I'm going to just write this down here. I'm going to project onto the xy plane. And at that point, all I'm worrying about is just the angle, right? I project down and I wanted to see what the angle is. I don't care about radius. Right, that's my theta. So it's the same exact thing. For this phi here, we are going to project onto the xz or yz planes. Okay? And if I project it on there, if I project them on there, I can actually start to think about what that angle is at a more formally. And so if I project it, just kind of showing you here, just to kind of think about this, what I do is I project this onto the xy plane. I'm going to move this down a little bit. If this is the xz plane, let's say I project this onto the xz plane, this is my phi right here, okay? This is my phi. And so if this is my phi, I have phi equal to 0 here. This is phi equal to pi over 2. This is phi equal to pi. Now, you can either go either way. You can go counterclockwise or you can go clockwise, whichever direction you want. It doesn't really matter because the theta direction is going to cover it. The theta direction is going to cover the sweep if you want. So if I had like a half a hemisphere, right, all above the xy plane, it would be from 0 to pi over 2, as an example. Now, the big thing when we change to spherical coordinates, as you will see in the lab, and as you've probably seen it too, I kind of make you go through this part, just kind of show you it. The big thing to kind of change here is I have these coordinate shift transformations, right? I have that x is equal to rho cosine phi, cosine theta sine phi. I have y equals rho sine of theta sine phi, and I have z equals rho cosine of phi. I also have this nice transformation too, when I have rho squared equals x squared plus y squared plus z squared. We also do have these restrictions. So just go ahead and make sure that you are comfortable with these transformations. You don't have to be, I'll talk about probably in another video, the full geometry of how we get these, just so everybody's kind of aware. But it's pretty important to just remember that when I do change here, I do have to change a lot. And the big thing too, when I do change it, is to think about also that the differential volume here is actually rho squared times sine of phi. So when I transfer over here to a volume, when I transfer over to spherical coordinates, I need to go rho squared times sine of phi. The reason why we need this rho squared here is because I need to have a volume, right? And this is my only length. These two are angles. So to kind of have dimensions match up of that length to the third, I need that length squared here. The sine of phi is for another reason and a little bit more technical reason, but I won't kind of go over that. So whenever I'm transferring, right, I need to exchange my function value for all my variables, all these other shifts. So what I do here again, as in this case, if I want to integrate over this region, which I've come up with, so make sure you read all that through. You kind of create this function. I created this function and I'm replacing my x coordinate with what I have up there. I'm using rho, I'm using r, and I'm using phi as p. Feel free to use whatever letters you want. This is at least my opinion on how to do it. The y is rho sine of theta sine of phi. And then lastly, we have rho cosine of phi here. And we have to multiply it by rho squared times sine of phi. And then we have our limits. We will most likely never have any variables in our limits of integration for spherical coordinates. That becomes very, very difficult. That's a really high level problem. The only thing you might have would be with rho. Other than that, it's pretty rare. Honestly, which is pretty rare. It's probably a better coordinate system to use then if that happens. So in this example, we kind of ask you to draw stuff out and kind of visualize that, and hopefully you'll be able to do that from there. Remember that the volume of E is just with an integrand of 1. Right? It's an f of x, y, z is equal to 1. But please make sure that when you transfer over, you still need this rho squared sine of phi. And lastly here, what we do with these application of triple integrals is when I have this center of mass here. So the idea is if I tell you basically that I give you a function, let's say I have this object here, and I give you a function value at every single one of these points. You can think about the density at every single one of these points here. If I integrate it all over this, I can get the mass of the object. But what if I want to find the center of mass? You could think about maybe what the fulcrum would be if I thought about the two-dimensional. Like, where's the fulcrum here? Where's that center of mass? Because maybe there's different densities at different parts here. Maybe I'm changing material or something like that. How we calculate this is as follows. The mass of the object is honestly just the triple integral with that density function. But to calculate the actual center of mass, the actual point that is the center of mass, what we do is we take x times that function, y times that function, z times that function. So what you divided by this mass. So the first thing you always want to construct is what the mass of the object is. Define that as a variable. Define that as mass is equal to, or something like that in Mathematica. And then what you do is I'm going to calculate Cx, which would just be x multiplied by this function value, which in this case would be x squared plus y squared plus z squared. Y times that and z times that, and making sure that you use these limits of integration. A is just a random variable. It's just a variable that you want. In this case, it's just a regular variable. Leave it as a. Don't change it to anything. Your answer should have a's in it. And yeah, so you're going to get a coordinate, which is a cx, cy, and cz. So just make sure you adequately represent that. So yeah, again, this is going to be due Sunday. It's a little bit longer. There's not a lot to do. I mean, there's a lot of exercises, yes, but there's just a lot of reading just on top of it. So yeah, it is a little bit long, but hopefully it'll help you guys out, especially getting ready for that midterm. If you have any other questions, please let me know. And yeah, I hope you're doing well. Happy Earth Day. Maybe go outside for a little bit and just kiss a flower or something. I don't know. or don't drive. Something like that. All right. Enjoy the day, and let me know if you guys have any other questions, and I'll see you soon.